All right, guys. Hello. So I'm gonna do, of course, a review, and I thought I should begin with maybe some problems uh, in chapter 5, and then go back to chapter 1, and start with limits. Of course, uh, I'll take problems from the list. If you have questions from that list, please in the chat box, let me know what number you want me to go over. But I thought it's best that I begin with a area volume problem. I think a couple of problems would be sufficient. So let me go to section 5, maybe 5.2. And we'll take a problem, we'll do everything with that problem. Okay, we find area volume using all methods. All right, so for section 5.2, let's go with number 17. Okay, so this problem is giving you a region. They say the region is bounded by the graphs of y equal to x squared and y equal to 2x. All right, and they say that the region is revolved around the y-axis. So instead of revolving the region around the y-axis, I'm going to revolve it around a few axes. And I'm also going to find the area of the region as well. Okay, so let's just get an idea of what approximately this region is going to look like. We have y equal to x squared, which is a parabola. And we have so again, remember, you want to roughly graph the picture, and then we're going to graph an accurate version of it. Y equal to 2x is a line like that. All right, so we know that the parabola and this line intersect to form this region. Let's find the points of intersection first. You're going to just locate or equal the two functions, x squared equal to 2x. To solve this equation, you need to move 2x over. You get x squared minus 2x equal to 0. You can solve this by inspection if you want. You can. 0 is going to be a solution right there. And also 2 will be a solution. If you put 2 for x, you get 4 equal to 4. But if you want to solve this algebraically, you need to factor out an x. You get x minus 2 equal to 0. So intersection will happen when x is 0 and x is 2. Okay, it would be beneficial to get also the y values when x is 0, y is equal to 0, and when x is 2, y is going to be 4. Okay, just put 2 into here, or here you're going to get 4. So points of intersection are 0, 0, and 2, 4. Okay, now we can graph an accurate version of this region. And let me move this down. So we have 0, 0, and 2, 4. We have a parabola. Again, you don't need the full thing. And the line. We don't need the whole thing, guys. You don't need to draw all graphs perfectly or completely. We just need the part that is bounded by the two graphs, and there we have the region. Let me just shade the region. And then I'm gonna reuse this graph for several problems. Okay, so let me just copy.
It's recorded, so it's okay.
Yeah, I'm recording. We are recording. Okay, so guys, let's begin by finding the area of the region. Okay, because this is what I could do exactly. I can give you I'll take the liberty of muting you myself. Guys, if you have question, please type it in the chat box. If you want to ask your question, unmute, ask me your question. I'll be happy to answer. Okay. So again, point here is 0, 0. And there it is 2, 4. All right, so let's begin finding the area of the region. And I want you to just set up integrals and not evaluate the integral itself. Let's set up an integral for the area with respect to x. Okay, I'm not going to do volume yet. We'll just do area and then we'll do volume. So do integral for area with respect to x. Okay, so to do integral with respect to x, you need to take a vertical strip, as I have shown in class. Okay, we take a vertical strip because the width of the strip, if you notice, the width of the strip is an increment of the x-axis. It's an increment of x. Okay. So here's that vertical strip. All right, it has dx as its width. Okay, we need to find the height of the strip. The height depends on the top and bottom that bound the strip. The bottom of this rectangular strip is on the graph of y equal to x squared. And the top is on y equal to 2x is the equation of that line. Okay, so the height of the strip is going to be top y minus the bottom y, 2x minus x squared. Okay, so we have both length and the width of that rectangular strip that we're going to add to find the area. Here is the integral. Okay, now look at the region, these strips. If you were to partition the region doing Riemann sum, these strips begin at x of 0 and end at x of 2. Okay, so x goes from 0 to 2, and we have height, or we have length times width. Okay, so that's the length and the width is dx. Okay, and that's it. That's the integral. So let me put that over here. And there's the integral. So again, in or within the region x varies from 0 to 2. And that determines the bounds of integration. Okay. All right, so let's do a setup for the integral for area, but this time with respect to y. Okay, so again, you want to graph the region once again. Oh, I forgot, I erased the I copied something else, so it erased it. But you need to redraw the region if you can't see it. Okay, and this time we need to take integral with respect to, so again, it's the same region, with respect to y, which means that the strips have to be horizontal. Because when you draw a horizontal strip, that strip is going to intersect the y-axis, and therefore that increment is a dy. Okay, so remember, for area, vertical strips give you dx, horizontal strips give us dy. So again, that increment is just a dy. Let's draw that strip out again. Okay, so again, the width is a dy. Now, to find the length of this rectangle, guys, you need to take this point, do minus this point. These are x values. This is the right x, this is the left x, right? Top, bottom, those are y's. Right, left are x's. So you need to take these functions and solve for x. Okay, so again, since the length of the rectangle is right minus left, we need to express the functions, or we need to, let's say, solve the functions for x. Or you can think of it like this. Since the integral is with respect to y, then these have to be expressed in terms of y. Okay, dy, we should have functions of y. So let's go with the line. The line is y equal to 2x. Solve this for x, just divide by 2, and you're going to get x equal to 1/2 y. And the parabola, which is y equal to x squared, solve it for x, take square root. When you take square root, we get a plus or minus, guys, we get a plus or minus root y. Okay, if you take the square root, you get plus or minus root y equal to x, or you get absolute value of x equal to root y. So what does that mean? The plus root y describes the right parabola. Negative root y describes the left parabola. If x is equal to negative something, then you're looking at negative x's, which is not what we are concerned with. We are looking at the right arc of the parabola. So here x is just equal to root y. Ready? So I am going to call the blue graph x equal to root y. The green graph is x equal to 1/2 y. Now we are ready to find the length of this horizontal rectangular strip. Okay, so the left is on the green graph, which is x equal to 1/2 y. And the right of the rectangular strip is on the blue graph, which is x equal to square root of y. Okay, so the length of this rectangular strip is right minus left. The bigger x minus the smaller x. Okay, the bigger x is root y minus the smaller is 1/2 y. Always right minus left. Okay, always up minus bottom. Top minus bottom if it's vertical, right minus left if it's horizontal. So the area is going to be the integral from, I'll write that in second. The length is root y minus 1/2 y. And the width is dy. Okay, now within the region, the y values range from 0 to 4. Alrighty, maybe I could use let me use a different color on that. From 0 to 4. 0 to 4. And yeah, let me also change the color for the x's of the integral with respect to x, which was from 0 to 2. And that's it. Okay, so both integrals are equally easy, I would say. It doesn't really matter if you switch the order of integration like we did, you know. I would say this integral is easier to calculate, but they both give you the same exact thing. Okay. You could try it out. You could evaluate these two integrals and they're exactly going to equal the same value. Okay, so let's go ahead and do some volume by revolving this region around different axes. That should be like another 20 minutes of stuff, but it's totally worth it. Okay, so here we're going to find the volume by revolving the region around let's go with the x-axis. Okay. So I'm going to, again, guys, you need to again draw the region. There's the region. Let me, yes. Yeah, so when drawing, when revolving around an axis, and I'm gonna tell you what method to use here also. Okay, so we're gonna use here the washer method. Disk or washer method. This is definitely washer because as this region goes around the axis, it's going to create, there will be a hole basically. Okay, there's like some empty space right here. So we're looking at the washer method. Okay, so when revolving around an axis using the washer method, if you're revolving around the x-axis, just like previous problems, what you want to do is to take a vertical strip like that, and you don't need to draw the full region again, guys. Just revolve that strip around the axis like this. Let me just move that point over. It's getting too crowded. Okay, so when revolving that around the x-axis, it's going to create a washer. Okay, again, there's some empty space. Like that. Okay, so now what you want to do is draw that washer out. Right there. And you want to immediately tell what the center is. Okay, so the center of this thing is just y equal to 0. Okay, and what we need to do is we need to find the outer radius and the inner radius. Okay, so the outer radius is as you see on the green graph, right? This is the most outer edge, which is on the green graph. Okay, so you can call this R radius out, or I wrote as R big. It doesn't really matter. This is on the graph of y equal to 1/2 or y equal to 2x. Okay, the inner radius right there is on the blue graph. We call that R in. It's on the graph of y equal to x squared. Okay, now, yeah. Actually, guys, you know what? Actually, let me just be consistent with my lecture last time. Okay, just locate the, don't call them yet R. Okay, guys, don't yet call them R. I think what I said during the lecture is just get the y values corresponding. Okay, so the top edge is on y equal to 2x and the bottom edge is on y equal to x squared. Now find the radius. Okay, so we have the big radius. The big radius is from the center to the most outer edge. We call that R out. And all you got to do is subtract y values. Do 2x minus 0. Which is just equal to 2x. Okay? Yes. So 2x happens to be the outer radius, right? Now, sometimes again, the axis of revolution is somewhere else. If this is somewhere else, like let's say add 1, then you have 2x minus 1. So the outer radius is not always the top function. It depends on where the center is. Okay, then we have the inner radius. From the center to the inner circle, which is the blue minus the center, 2x minus 0, so 2x is the inner radius. All right, so we are ready to set up the volume integral here. Volume is always, remember, volume is the integral of pi times the outer radius squared minus the inner radius squared times dx. And remember that dx is the thickness of the washer. Okay, that we are finding the volume of the outer solid, subtracting the volume of the inner solid to get the volume of this solid. Okay, and yeah, so we have pi. The outer radius here is just 2x squared minus the inner radius of x squared. Okay, times dx. And the integral here again goes from 0 to 2. Right? X goes from 0 to 2. So that's the volume integral. Alrighty, let's change the axis of revolution quickly. We're going to revolve this thing around a different axis. Let's say y equal to -2. Okay, so let's again draw the region. Here's the region. Draw also the axis of revolution. Y equal to -2 is a horizontal line. Guys, I'm not honestly asking for too much, guys. I'm not asking you to do the integration, just the setup. Hopefully it's you know, you don't find it time consuming. You just have to learn the method. Okay, you got to do your graph correctly and know what a vertical line is, what a horizontal line is. Okay, so we're going around y equal to -2. So again, we take a vertical strip. Whenever you're doing the washer method, you know, I'm gonna write that as write the summary of these. Whenever you do the washer method, okay, if you are going around a horizontal axis, then we take a vertical strip. Let's actually summarize that, guys. Let me go to the next page and write down the rules. I was just kidding. So for volume, when revolving around a horizontal axis, Okay. You're going to draw a vertical strip. Yeah. And revolve it around that axis. To form a disc or a washer. All right, and here, this is suggesting that integration is dx. It's going to be with respect to x. A vertical strip, it increments the x-axis to dx. Okay, that is perpendicular to the x-axis, so we have a dx. I'm going to post the notes. Don't feel rushed to copy down. Okay, so again, we got a horizontal line. We want this to revolve around. We take a vertical strip. All right, now let that vertical strip go around. Of course, it's going to be a pretty large washer, but you don't need to draw the full solid. Just make sure you draw the washer correct to some extent. Yeah, I think I didn't go too high down, so let me. Again, your drawing doesn't have to be perfect. Whatever, it's good. So this is a washer. There will be a massive hole right there in the middle. Okay, here is the washer. Okay, so again, draw that washer out. It doesn't have to be as big. I do much better on pen and paper for some reason. Okay, let me fix the other one. Ready? Oh, come on, dude. All right, there we go. Okay, so yeah. All right, so immediately locate the center. Okay, here's the center. The center is always the axis of revolution. Y equal to -2. Okay. Write down the point on the outer circle. So this is the outer circle. That point is on the green graph, y equal to 2x. The inner circle is on y equal to x squared. Okay, as long as you've done this correctly, then you can hopefully get the inner radius and the outer radius. And once you get that correctly, then the hard part is done. All right, so the outer radius is from the center to the outside circle. Okay, and that is 2x. It's always, guys, always top minus bottom. 2x minus -2. Okay, so that gives us 2x plus 4. I'm sorry, what am I saying? 2x plus 2. 2x plus 2. That's the outer circle, and or the outer radius. The inner radius is from the center to the lower circle. Okay, which is x squared minus -2. All right, which gives us x squared plus 4. I said it again, x squared plus 2. That's the inner radius. So again, you do pi r squared for both, subtract. Okay? Volume is equal to, you could put the pi out of the integral. The integral of the outer radius, which is 2x plus 2 squared, pi r squared, minus, exactly like the last integral, minus the inner radius squared, which is x squared plus 2. Don't forget to square. It's that times the thickness, which is dx, and once again, within the region, x goes from 0 to 2. All these washers, guys, if you were to draw all washers, all of them for the solid, the very first washer starts at 0, the very last washer stops at 2. Okay? Yes, so there, that is your integral. Okay, so let's now revolve around a different axis. Let's revolve around. I was gonna revolve around y equals 0 or x equals 0. Let's revolve it around a vertical axis. It doesn't matter what that vertical axis is. It could be around the y-axis, or it could be around x equal to -1, but let's revolve it around x equal to -1. X equal to -1 is the vertical line going through x of -1. Okay, so again, our region, and I need to extend the x-axis a little bit. Okay, so let me just erase the part I don't need. X equal to -1 is right there. And there is the axis of revolution going around. Alrighty. So let's see, guys. If you were to take a vertical strip, there's your vertical strip. When that thing gets revolved around, it's not gonna create a washer. Okay? As this goes around, it will create a cylinder. Okay? And that's not what we want. There is a method, this would give you the volume using cylindrical shells, but we want the washer method. Okay, so again, these are all washer methods. Okay, yes, so what does the rule say? The rule says when revolving around a horizontal axis, and that's not what we are doing. Okay, when you're revolving, so the opposite of this, when you revolve around a vertical axis, you want to draw a horizontal strip. Okay, let me show you. That's the region. All right, let me draw. Let me copy this so I don't keep erasing. All right, so look, if you take a vertical or a horizontal strip like that, just imagine what happens when that little segment is revolved around. As this goes around, it does create, look at that, it does create a washer like that. Okay, massive hole right in the middle. So rule says you just have to change the statement. When revolving around a vertical axis, draw a horizontal strip and revolve it around again that axis to form again a disc or a washer. A washer is two discs being subtracted, basically. And guess what? Here integration is going to be with respect to y. It is a horizontal strip. A horizontal strip is an increment of y. Okay. The thickness of that washer will be a dy. So we have to express these as functions of y. Let me write that here also. So you're gonna solve each equation for x to express in terms of y. Integration is with respect to y, and you're looking at a horizontal strip. A horizontal strip is right x minus left x. You have to have x equal to whatever. Okay. Sometimes when you're given a problem, the functions are already in terms of y. You don't need to solve them. But we've already done this. We have the line, which is x equal to half y, and the arc of the parabola, which was x equal to root y. Okay. All right, so let's do the revolution. All right, so again, this is just gonna revolve around. Do your best to draw the washer. You could even draw half of it, guys. I don't know why I'm drawing the full thing. You don't need to draw the full thing. You can just draw half of it, honestly. You just need the bigger radius minus the smaller radius. You don't have to draw the full thing if it annoys you. I mean, it does annoy me a little bit because I'm not so good at drawing circular stuff. But Yeah, that is supposedly the washer. Okay, so draw the washer out because you want to identify the inner radius and the outer radius. And again, the rule is that you immediately want to label the center. Okay. Center is an x of -1. You already see that this is x equal to something. X equal to something. Horizontal strip x. Okay. Yeah, so the point on the outer circle, this point is on the blue graph. Okay, so here, x is equal to √y. And the point on the inner circle is on the graph of x equal to 1/2 y. All right. And again, the center is x equal -1. So, and I know what I could also do, I could make the outer circle blue if you want, because it's generated by revolving the blue graph around that axis x equal to -1. But now the outer radius is from the center to the point on the outer circle, okay, which is right minus left. The bigger x is this, the smaller is that. We do √y minus -1. Okay, so that is just x equal, that's √y plus 1. That's equal to the outer radius. All right. Try again. Yeah. And the inner radius is from the center to the inner disk, which is the right x. Right x is 1/2 y. Minus the left x, -1. So we get 1/2 y plus 1 for the inner radius. Okay, and again, you just do the integral of pi r squared, subtract for the volume. Put the pi out, the integral of the bigger radius or the outer radius, √y plus 1 squared minus always the inner radius squared, 1/2 y plus 1 squared. Okay, and you multiply by dy, because again, looking at the washer, thickness of that washer, this washer has some thickness. The thickness is dy. Okay. Yeah, so this is the area of the washer times the thickness of the washer gives you the volume of the washer. And again, within the region, y starts at 0 and ends at 4. Okay. So we have the bounds of our definite integral, 0 to 4. Okay, guys, notice that the volume here is not the same as the volume here. These are two very different solids. Okay, they are formed very differently. All right, let's see now. So we are good with the washer method, guys. Let's also do the shell method. All right, so we are going to. Yes, let's revolve this thing around x equal to -1 again, guys. Okay, but this time we're going to use the shell method. So that's part F of the problem. Around x equal -1. And we're going to use the shell method. Okay, here is the region again. Please, guys, don't mess up the graph of the region. Okay. All right. So, yeah, if you want to form shells, let's write the rule down. Let me just cut this and put it somewhere else. Okay, so this is, these are rules for washer disk methods. Rules for the shell method. Okay, when revolving around a vertical axis, so guys, let's remember the issue with the washer method that we just used right here. What is the issue? The issue here is that you have to solve your equations for x. Okay, because when you take that horizontal strip to revolve around, forming the washer, you have to have x equal to something. Horizontal strips, x equal to something. And in most cases, not this case though, but in some cases, I should say, we are unable to solve for x, right? This was easy. You just have to divide by 2. You just have to take the square root. But again, if you have y equal to sine of x, right? Solving this for x, you would get sine inverse of y, and we don't want to deal with that. Or you have, like, let's say y equal to x sine x. You definitely not solve this for x, man. You just can't. Okay, it'll be very, very, I don't think you can solve this for x. It'll be very, either impossible algebraically, or you just can't do it so easily. Okay, so we didn't want to deal with a horizontal strip. If you don't want to deal with the horizontal strip going around a vertical axis, then we take a vertical strip. When you take a vertical strip, right, top is a y value, bottom is a y value, so you don't have to solve for x. You can just leave it as y equal to f of x. Okay, so that was the situation. We want to take, instead, we want to take a vertical strip. But remember, when you take a vertical strip around a horizontal axis, it doesn't form a shell, it forms a washer. I'm sorry, it doesn't form a washer, it forms a shell. So when revolving a vertical axis, we're going to draw a vertical strip again. Why vertical strip? Because vertical strip will be a dx. We don't need to solve, we don't need to express in terms of y. and revolve it around that axis to form a cylindrical shell. Okay, and again, integration is gonna be dx. All right. And that's what we like. So let's go back. And that's exactly the situation we're dealing with. We have a vertical axis. We are revolving around that. So we take a vertical strip like that, and we revolve it around. And again, as that revolves around, it is going to create a cylindrical shell like that. Okay, again, you don't need to draw the full shell, guys. You don't need to draw the whole thing. Just draw half of it from, from the edge to the center, and that's sufficient. Okay, so again, this thing has a thickness. It's like, again, it's like a rectangular piece of paper, guys. Imagine again taking a rectangular piece of paper and forming a cylinder, right? Just bring the two edges together to form a cylinder is what you're looking at here. All right, so again, what you want to do now, just like before, is to draw this figure out. Draw the shell out as you have drawn washers out to locate, to determine the dimensions. Right there, again, immediately locate the center, like always. Center is at x equal to -1, okay? And just like before, locate the points on the upper, I would say, circle, and the point on the lower circle. The point on the upper circle is on the green graph, right? This point on the green graph gets revolved to form that circle right there. Okay, so again, this point is on the graph of 2x. Okay, or you can call that point x 2x. Also write down the x value of that point. The lower circle is going to be on the blue graph, so call that point, I need the blue, call that point x squared. Okay, so for this method, I'm not only writing the y value, guys, I'm writing also the x value, if you don't mind. So we are ready to now find the radius of this thing. The radius is the distance from the circle to the center, okay? And since from here to here, guys, is x, right? From here to here is x, then the radius is going to be the right x minus the left x. So you do x minus -1. Let me actually write that right below. There's more room here. Yeah, so that's x minus -1. Okay, so just imagine, guys, just imagine, don't think about this too much. Just imagine for a second, okay, that you draw this thing, you draw this vertical strip at x of 1, right? Just imagine this is at x, here x is equal to 1, right? So the distance from the circle to the center is going to be the total distance from the center to that point x, which will be 2, right? You do 1 minus -1. It'll give you a 2. That's given if you draw the shell at x of 1. If you were to draw the shell at x of 1.5, I mean, you get a different shell, but if you draw it at 1.5, then the distance from that strip to the center is going to be 2.5. You take 1.5 minus -1. That would be 2.5. So in general, if this vertical strip is at x, then we get x minus -1. Okay, which is again the radius. Right? So the radius of the shell, guys, is always. If you want to, you know, if you're good at memorization, if you want to remember it instead of trying to reason your way out of it, remember that the center of a shell is always x minus the center. Let me write that down here for you. Radius of the shell is always x minus center. Always. All right. So x minus -1, that's x plus 1. We also need the height of the shell. The height of the shell is the top y minus the bottom y. It's the vertical distance, top y minus bottom y. So we get 2x minus x squared. Okay, so we are done. We need these quantities to come up with the volume. All right, the volume of the shell is always going to be, I derived this for you. It's always going to be 2 pi times the radius. Okay, 2 pi radius times height times dx. Okay, which is the thickness. Right? 2 pi radius gives you the circumference of this thing. The circumference times height times the thickness is going to give you the volume of this shell. So V is going to be 2 pi, radius is x plus 1 times the height of 2x minus x squared. Okay, times dx. So one more time, guys, 2 pi radius height dx. That's what the rule says. Do the integral here from, once again, 0 to 4. Right, within the region x goes from 0 to 4. I mean, if you break the region or if you break the solid into layers of shells, these shells start at 0 and they go all the way to 4. Okay, and that gives you the volume. So if you find this integral, guys, find this integral and this integral, they are exactly the same. Okay, they have exactly the same value. Which is easier to do? Definitely this one. Okay, because this integral, you're required to square these things, right? You have to square that, you have to square that, you have to combine terms and then do the integral. Whereas here you just multiply x plus 1 by 2x minus x squared, FOIL it out, and then integrate term by term. This is a little easier. All right. That's the shell method. So I can, on the final, ask you something very similar. Right, just the region bounded by two graphs, you'll be asked for area with respect to both x and y, and you're gonna be asked for the volume setup using shell, using washer around both axes and using shell method around a vertical axis. Questions, guys? Does anyone have any questions from the list of problems they want me to go over? It'd be great if you could redo the same problem. So good, let's go back to section 1.6 and take a couple of problems from that section. Okay, section 1.6, limits. Guys, knowing limits is a must getting out of Math 7. So let's just discuss numbers. I'm not going to be able to do every problem here, but I want to discuss number 31 and 27 quickly. Let's go with 27. Which is the limit as t goes to 0 of root of 1 plus t minus the root of 1 minus t over t. Okay, as t goes to 0, what happens is that you get an indeterminate case. When you put zeros here, you have 1 minus 1, that's a 0 divided by 0, indeterminate. So you can't say limit does not exist. We have to try to redo the problem or do the problem, rewrite it algebraically. When you have square roots involved, you're going to do the opposite of simplification. You're going to multiply by the conjugate on both top and bottom. The conjugate is always going to be the same thing, but the sign of the middle will be opposite. Okay, so we're going to have a plus. Multiply top and bottom by the same thing. We call it again the conjugate. The reason we are multiplying it by, by the conjugate is that if you have the difference of two terms, a minus b, and that's what we have here. We have a minus b. When you multiply a minus b by a plus b, then you're looking at the difference of two squares. If you FOIL this thing out, you're going to end up with a squared minus b squared. Okay? a squared minus b squared if you FOIL this out. And the good thing about a squared and b squared is that it makes square roots square root less, okay? Yeah, we get the square of that minus the square of that. The square roots go away. Guys, again, on almost every test, I saw people not writing their limit down in the next step. If you don't write your limit down, it's gonna be points taken. Okay, write down the limits. Don't just say equal to and then write down the expression because that makes no sense. Right, so we have 1 plus the root of 1 plus t squared minus the root of 1 minus t squared. In the bottom, you have t times, guys, please do not multiply t in, just write t times the conjugate. Again, do not distribute this in. The reason we don't want to distribute it is because we want this t to cancel out. It has to get canceled because it is contributing to the 0, right? When you put 0 into t, you get 0. We want that t to cancel out. So when you multiply the t in, how are you going to cancel it out? You have to factor it back out. So just don't multiply right from the beginning. Write the limit. Don't forget writing the limit. Okay, so here we have 1 plus t minus 1 minus t over t times . Okay. Add like terms to simplify. Don't forget the limit. Alrighty, so on the top we have 1's canceling out, 1 minus 1. We have a t minus negative t. That's 2t. You see, we have a t now on the top. That's going to cancel the t in the bottom. Right? We can cancel out factors, not terms. I mean, you have no idea how often I see people in your class canceling this t with that t or with that t. You can't do stuff like that, guys. You just can't. This is a factor on top, which cancels this factor on the bottom. So the factor that gave us the 0 over 0 is now gone. Don't forget to write the limit down. We have only root of 1 plus t plus the root of 1 minus t. Now we can plug 0 in. Okay, plug 0 in. On top, you just have 2. Bottom, you have root 1 plus root 1, which is 2. 2 over 2. We have a limit of 1. Okay. Once you plug the value of the limit in, you don't write the limit anymore. All right. The limit has been evaluated, so we don't write down the limit and we plug in the limit at the same time. Limit of 1. Okay, problem 39 in that section says that you have a function f of x that is bounded by 4x minus 9 and x squared minus 4x plus 7. We don't know what f of x is. We just know that f of x is between these two functions. Okay, and they ask you to find the limit as x goes to 4. Right, we don't know what f of x is. We don't. But since it's squeezed by these two, then we can take the limit of these. Take the limit as x goes to 4 of 4x minus 9. This is a polynomial, so you can just plug 4 in, you get 4 times 4. You see, once you plug in the value of a, you don't write the limit anymore. 16 minus 9 is 7. Also do the limit as x goes to 4 of the right bound, x squared minus 4x plus 7. Okay, so that gives us 16 minus 16 plus 7, that's also 7. So here the limit of f of x is squeezed between 4 and 4, therefore it has to be 4, okay? Yeah, this implies that the limit as x goes to 4 of f of x should also equal to 4 by the squeeze theorem. Okay? If the limits are different, if the limit of this function was 4 and the limit of this function was 7, then we don't know. We can't tell what the limit is, guys. We won't be able to tell. No problem, Darren. You can watch the recording later. So that's section 1.6, guys. You got to be thankful I'm not asking you questions from section 1.7. Epsilon delta definition, you don't need to worry about that. Section 1.8 is on continuous functions. Most people did very good with continuous functions, I believe. So just make sure that to show f is continuous at x equal to a, we need to show 3 things. Number 1, f of a must exist. Number 2, limit as x goes to a of f of x must exist as well. And 3, the limit as x goes to, or I should say f of a, and the limits of the function at a must be the same. If they're not the same, then what did I say? I wrote, you're right, I wrote 4, it should be 7. 4, 7. I don't know why I did that, saying. Yeah, people are like, what the heck? Yeah, so these 3 things need to be shown, guys. If f of a doesn't exist, if the function does not exist at a, then the function can have a hole, or it could have a vertical asymptote. And at none of those, the function is continuous. If the limit does not exist, then the function can jump, right? At a jump, the limit from left and right do not equate, so limit wouldn't exist. And if the last condition doesn't meet, then the function can have a removable discontinuity, right? So here we have a function whose limit is something and value is something else. Removable discontinuity. Let's see here. All right, let's go with this function. Here the question is f continuous at x equal 2? Because it's at 2 that things change. We have a piecewise function where 2 is happens to be the boundary point of all pieces. Okay, so first of all, we check number 1, f of 2 is equal to 3. It exists there, right? At 2, y is 3. Okay, now we need to find the limit. This is a piecewise function. Pieces change at 2, so we need to find the limit as x goes to 2 from the left for f of x. From the left of 2, we need to take this piece. This reads as x less than 2, left of 2. So we take 2x minus 1. 2x minus 1 is a polynomial, so you could just plug 2 in. You get 2 times 2 minus 1, that's equal to 3. Okay, take the limit of f of x as x goes to 2 from the right. Okay, right of 2 is greater than 2, so we take x squared minus 1. Again, x squared minus 1 is a polynomial, plug 2 in. That gives you 3 also. Okay, so the limit as x goes to 2 of f of x is equal to 3. Limit exists also, guys. It's equal from left and right. So this function has no jump. It has no asymptote because we didn't get infinity. But now the limit and the function are not the same at 2. F of 2 is not equal to the limit, is it? Oh, it sure is. It actually is equal to, wow, what a coincidence, man. I made up this problem and it worked. So f of 2 is equal to the limit as x goes to 2. They are both 3. Okay, so here f is continuous. Therefore, f is continuous at x equal to 2. Okay, so make sure you can't use the definition of a limit. Let's move on to chapter 2. I'll try to do as many problems as I can. Chapter 2 is mainly about derivatives, guys. I've noticed on your exam, a lot of you guys are not using the chain rule correctly or not using the chain rule at all. And that is very, very scary, guys. I can't have you guys move on to Math 8 while you can't do a simple chain rule. So this is your chance, guys, to perfectly understand the derivative rules. If you're in calculus 2, calculus 3, and you have to do a math problem where you take the derivative. If you don't use the product rule where you should use the product rule, or if you don't use the chain rule when you should be using the chain rule, you are not gonna, unfortunately, you're not gonna survive Math 8, Math 11, Math 15. And your teacher is not gonna be happy with you and me, okay? I certainly don't want to have someone who doesn't know chain rule take my Math 11 or Math 8 class. So guys, please be mindful of that. Don't rush through the problems on the test. Don't get excited. Just be very, very careful. Make sure you are using your derivative rules properly. So let's see here. I want to do a derivative definition here. So this is section 2.1, problem 19. Okay, this has got nothing to do with chain rule or product rule. This is definition of derivative, and that's something you need to know. Okay, use the definition of derivative to find f prime of 6. Okay, if f of x is equal to the square root of 4x plus 1. Okay, we want to find the derivative at 6 for that function. So let's recall the definition of derivative at a point. This is derivative at x equal to a. Okay, it is f prime of a equal to the limits of f of x plus h, or actually, let me think here. So it's f of a plus h minus f of a over h. Okay, this is the definition of derivative as h goes to 0. You can also first do f prime of x, do f of x plus h minus f of x over h, and then plug a in it. You can do that as well. Okay, so here we are calculating f prime of, they want it at 6. F prime of 6 is by definition limit, always h goes to 0 of f of 6 plus h minus f of 6 divided by h. Okay, so plug in. All right, so here is our function. To calculate f of 6 plus h, all you have to do is replace x with 6 plus h. Okay? So we get square root of 4. X becomes 6 plus h. Okay? Yeah. And then we have a plus 1 inside that square root. Yeah, I could change the color if you want. Give me a second. Yeah, x gets replaced by 6 plus h. Okay, minus f of 6. Replace x in the square root with 6. So we have 4 times 6 plus 1 all over h. Okay, guys? Yeah, and the rest is just algebra. Again, guys, this is a limit. Do not forget to write your limit at every step until the very last step where you're plugging 0 for h. Okay, let's do the little stuff with the math here. We have 4 times 6. I'm just trying to simplify this thing. We have 4 times 6 is that's a what, 24. Then we have 24 plus 1, which is 25. We also have 4 times h. So inside that first square root, we have 4h plus 25. Okay, minus square root of, well, the square root is gonna simplify, square root of 25. Right there, square root of 25 is just 5 all over h. So now question is, what is going to happen? So guys, I didn't do anything calculus yet. I just did what I have inside the root. 4 times 6 plus 1, 25, and 4 times h, 4h. Okay, now we do the calculus. If you plug 0 for h, what is going to happen? This will go away. You get root of 25. That's a 5. 5 minus 5 is 0 over 0 for h. Indeterminate for sure. These are all going to be indeterminate. So you have to multiply by the conjugate. And the conjugate, as we said, is always the same thing. Square root of 4h plus 25, but the opposite sign. Minus 5, you write plus 5. That's the conjugate. Divided by the same conjugate. Just like that very first problem that I did in limits. So once again, we have the difference of two squares. Don't forget to write the limit down, as I said so many times already. It's getting on your nerves probably. So difference of two squares says a minus b, a plus b is a squared minus b squared. And in the bottom, do not multiply that h in. Okay, again, this is exactly like this problem here. Okay, so squaring is going to cancel out the roots to get 4h plus 25 minus 5 squared, 25 over cancel out the 25s. We have the limit as h goes to 0. Don't forget the limit. 4h. Okay, so we have a 4h over that whole thing, right? With these being gone, we have this factor h canceling this factor down there. So cancel those already. That h goes with that h. So we have the limit of 4 over square root of 4h plus 25 plus 5. All right, now let h be 0. Okay, I'm evaluating the limit at this moment. I don't write the limit down anymore. Okay, we are evaluating. Drop the limit, plug 0 for h. You get root 25 plus 5. That's 4 over 10. Root 25 is 5 plus 5, 10. So that reduces to 2/5. That's the limit. Okay, there. Done. 2/5. Okay, now, well, by now you have learned the laws of derivatives. Okay, you all know how to calculate derivatives without using the definition of derivative, so you can check. Okay, see, we didn't have that capability in the beginning, but we now can take derivatives using the power rule, chain rule, you know, whatever rule. So here is how you check. Okay, so again, the function is 4x plus 1 in the square root. All right, You could think of that as 4x plus 1 to the power of half. Take the derivative. You got to use the chain rule. F prime of x is bring the half forward. 1/2 4x plus 1 to the power negative half. Chain rule. We have to do chain rule. Multiply by the derivative of 4x plus 1. Which is equal to 4. Already 4 and 2 reduce to 2. And you can move that square root or the negative power down to the bottom to get 2 on the top and square root of 4x plus 1 on the bottom. Okay, this is the derivative function. Already now plug 5 in it because original problem asked you for f prime of 5. F prime of 6, was it? Yes, 6. Put 6 in there. In the derivative function, that would be 2 divided by 4 times 6 plus 1. 2 over square root of 24 plus 1, 25. Square root of 25 is 5. It checks, okay? 2/5. You gotta be able to use definition of derivative to calculate. I'm not gonna be asking you to use the definition of derivative to find the derivative of, like, let's say secant x. Or the derivative of sine squared x. Or the derivative of x over x squared plus 1. Just some, simple function like that. Yeah, but you gotta be able to use the definition of derivative, and you gotta be able to take the derivative using shortcuts. So let's see, I'm just jump here. I see from 2, 3, you have one problem. Why? Let's go. Let me do some actual derivatives. Maybe 2, 5, where you have the chain rule. All right, so 2, 5, you gotta do. I have a bunch of problems. 19. We have 19, 23. Is good. 29. I'm trying to see which one. Let's do. Let me see, guys. Let me close the door. Let me see. Alrighty, let's do 29. Okay, which is the derivative with respect to x of cosine of secant of 4x. Cosine of secant of 4x. Okay, we set the word of twice. You must use the chain rule twice. Starting with the most outer function, which is cosine. The derivative of cosine is always negative sine. And you keep the inside, keep the inside. Let me just quickly, this one time use colors. Cosine of secant of 4x. Okay, so the derivative of cosine of anything is the negative sine of the same thing, which was the secant of 4x. You keep the inside as is. You multiply now by the derivative of the secant of 4x. Okay? Yeah. So in the next step, you're just going to copy down everything before that d dx. There. I'm cheating here a little bit to save time. Copy down everything before d dx. Now you have a new problem. Okay, imagine you have like 2-3 derivatives in one problem. That's exactly what we are doing here. Okay, organize the process, guys. That will organize your thinking process. So now the derivative of secant of whatever is going to be always, you got to remember these derivatives, is going to be secant of that whatever, tangent of that whatever. Okay, derivative of secant is secant tan. Secant at 4x, tan at 4x. Okay, we got one more inner function here, which is 4x. You multiply by the derivative of that now 4x. Okay, so again, copy down everything before d dx. Write down everything before d dx. This is given that, you know, you're not doing the stuff in steps. Some people can just do this in their head. I suggest you don't. Just write down each step. So that last derivative, the derivative of 4x is just 4. And we are done. Okay, we are done. And I mean that when I say we are done, meaning that we can't do anything with that 4, guys. We can't multiply the 4 inside the tangent or put the 4 inside the secant. You can't. All right. I've seen people doing that in Math 7. It's a huge no-no. This is it. All you can do is put this 4 in. You can put 4 in front of the whole thing if you want, but that's all you can do. Just leave it. So that was problem 29. 33. I probably do 33. Okay, let's do 33. That's a good problem. The derivative of, we have the 4th power of 1 minus cosine of 2x divided by 1 plus cosine of 2x. Okay, and again, if you want to put the 2x in parentheses, if that helps you out, you can. Okay, so here we have the 4th power of. The most outside function is the 4th power function. So we got to take the derivative of the parentheses to the power of 4. You can just ignore everything inside. Imagine you have x to the 4. The derivative of u to the 4 is 4u. And me. Bring the 4 down. Take 1 away from that power. Okay, keep the inside as is. Now we need to multiply this by the derivative of that fraction. Okay, guys, I'm not gonna write the dx of that fraction. I'm just gonna go ahead and do the derivative of that fraction. That fraction or a rational expression is, or a quotient requires the quotient rule. The quotient rule is you taking the bottom, you squaring it. So we have 1 plus cosine of 2x in the bottom, which we always square. That's the quotient rule. Okay. Then we do, let me actually write out the quotient rule. We do the top's derivative, okay, times the bottom. Write this out, it's gonna help you. Okay, minus always, quotient rule always minus the top, leave the top alone, times the derivative of the bottom. So 1 plus cosine 2x, the derivative of that. Prime again means the derivative. Okay, now we're gonna do the derivatives. So again, everything before that fraction, you need to copy down again. Okay, and let's just do those derivatives. Write down the denominator, 1 plus cosine 2x squared. Please do not square that, guys. Don't. It's just gonna be a complete waste of time. Okay, just leave the bottom. Now we do this derivative. The derivative of 1 is 0. Let me just change the color on that. Yeah, the derivative of 1 is 0. Okay, the derivative of cosine is negative sign. So let me just take a note of that down here. The derivative of cosine of 2x is by, the derivative of cosine is negative sign, again, 2x. And this is where people forget the chain rule. When they're doing little parts, they forget the 2 times the derivative of 2x, which is 2. Okay, so there we get 2 sine 2x. Right, guys? This negative and this negative cancel out. All right, negative, negative cancel out. So we have that times 1 plus cosine 2x. All right, minus 1 minus cosine 2x. Same exact thing here, right? The derivative of, change the color on that. Yeah, so the derivative of 1 is 0. Again, the derivative of cosine 2x is, once again, negative 2 sine 2x. Okay. I hope that is clear for you. So let's continue. Okay, so let's do the multiplication here quickly. We have this 2 sine 2x times the first parentheses. That would give us 2 sine of 2x. 2 sine 2x times cosine 2x would be 2 sine 2x cosine 2x. Okay, and same thing with the next with this stuff. Multiply that negative 2 sine 2x in, and at the same time you can multiply this, distribute this negative through. Okay, so we have negative 2 sine 2x times 1. That's negative 2 sine 2x times by that negative to get a plus 2 sine 2x. Okay, and again, negative 2 sine 2x times that cosine 2x. We have, guys, we have negative, negative, negative. 3 negatives is going to give you a negative 2 cosine 2x sine 2x. All right, so just please be careful with the signs here, and then we can simplify things a little bit. We have 2 sine 2x, 2 sine 2x, those are going to combine, and the 2 sine 2x cosine 2x negative 2 cosine 2x sine 2x are opposites. They're going to cancel out, thankfully. So here we get four sine 2x over 1 plus cosine 2x squared. And that's pretty much it. Already, that's it. Nothing else we can do. Okay. The only thing you can do is to multiply that 4 and 4. You get 16, but that's it. Okay. Let's see here. What else do I want to do? So yeah, please, guys. What about the 2x? Let me see here. The 2x. Which 2x? This 2x? What about it? Yeah, okay, what about the 2x? Well, I mean, what are you what thoughts do you have about this 2x? 2x, you can't do anything. I did already. We did that. We did that here when I did find the derivative of the 2x when I did the quotient rule here. When you did the derivatives of, look at that. When you do the derivative of 1 minus cosine 2x, you get 2 sine 2x. Yeah, we've done that already. Yeah, guys, please do your chain rule. You guys need a lot of practice. For those of you who are listening to me through the video, guys, you need the most practice needs to be done with chain rule. Okay. So let's move on. I want to get to at least related rates before ending today's session. Hopefully we're going to meet again. So section 2.6 is on, yes. So question is, what if it was x squared? So again, when we did the derivative of, yeah, so you did the derivative of the outside, you bring the 3 down, right? When you did the derivative of the inner part, which involved cosine 2x, we use chain rule for 1 minus cosine 2x. We did the chain rule. We did the derivative of cosine, which is negative sign, and then the times it by the derivative of 2x, which is 2. Okay, so if this was an x squared, right? If that's an x squared, when you do the derivative, you're gonna be multiplying by the derivative of x squared, which would be 2x. Okay, that chain rule that you're talking about is done right there. The cosine of 2x is sitting within the quotient rule. Right? It is sitting here. So we've already done the derivative of it using chain rule. Yes, exactly. We did it in the quotient rule. We don't do a separate derivative for that. Let's do an implicit differentiation, section 2.6. Let me see what problem is good. Oh, this is a good problem. Problem 26, I think I marked it as something we should do in section 2.6. And it says we have an implicit relationship. We don't. This equation does. Tangent of x plus y plus secant of x minus y equal to 2. So this is an implicit relationship. And they want you to find, oh, this is good. Question is to find the equation of the tangent line at, they give you a point, they should give you a point, pi over 8, pi over 8. They give you both x and y of this implicit relationship. If you graph this, guys, graph this on GeoGebra, I have no idea what this graph is going to look like. It's a graph, okay? It's some curve, and at pi over 8, which is a point in the xy plane, but right, like let's say this is the curve, we want the equation of that tangent line. Okay, so the equation of the tangent line requires the slope of the tangent line. Slope of the tangent line is the derivative, always, dy dx. So you're gonna begin by finding dy dx. So how do you do that? You take your equation, take the equation, take the derivative of every term. We take the derivative of the left-hand side, the derivative of the tangent of x plus y. We take the derivative of secant of x minus y. And on the right hand, we take the derivative of 2. dx means take the derivative of. We took the derivative, we're taking again the derivative of the equation, which means you take the derivative of every term. Okay, the derivative of tangent of anything is the secant square of that thing. So let me start here. Secant squared of x plus y. But don't forget chain rule. You got to multiply by the derivative of x plus y. The derivative of x, the dx of x is dx dx. Dx dx is just 1. The derivative of x with respect to x is 1. We have plus. The derivative of y with respect to x is dy dx. It's not 1. You can also write that as y prime. Okay? Likewise, the derivative of secant of x minus y is the derivative of secant of anything is secant tan of that thing being x minus y. The derivative, remember, the derivative of secant theta is secant theta tangent theta. Now you need to multiply by the derivative of x minus y, which is once again 1 minus dy dx. The derivative of 2 is 0. 2 is a constant. Okay, I mean, this is a lot of algebra, unfortunately. Man, a lot of algebra. But it's okay, guys. It's okay. The algebra is not bad. Here is why. Okay? We need to find dy dx. Guys, listen. You need to find dy dx. That's the unknown. So you have two options. The worst thing you can do is solve this equation for dy dx. I mean, me looking at it, I get a panic attack. I seriously do. Dy dx is right there, and we need to isolate that. Don't do it. Okay? It's gonna be too difficult for anyone. So here's what you can do, guys. Plug in the points. Okay, plug in the points. Plug pi over 8 for x, pi over 8 for y. We can do that because we've already taken the derivative. I can't, guys, we can't put pi over 8 into the equation first and then take the derivative. That makes no sense. Because when you put pi over 8 in here, you get a constant. The derivative of constant would be 0. You're not going to get an answer. We have taken the derivative. This equation has the derivative in it. So I can evaluate this equation at the point. Okay? So apply pi over 8, right? Basically, x is pi over 8. Y is pi over 8, thankfully. So this equation becomes secant square of pi over 8 plus pi over 8 is pi over 4 times 1 plus, let me just write that as y prime, plus secant of pi over 8 minus pi over 8 is 0. Okay, times the tangent of 0. That's good news, guys. That's good news. Tangent of 0 is 0. Okay, times 1 minus y prime, and it's all supposed to be 0. So again, since tangent of 0 is 0, then this whole thing is going to drop out. Secant 0, tangent 0, 1 minus y prime, that whole thing is going to get zeroed out. All right, so we have secant square of pi over 4. Secant of pi over 4, remember, cosine of pi over 4 is root 2 over 2. Okay? Yep. So when you square it, cosine squared of pi over 4 is root 2 over 2 squared, which is 2 over 4, or 1/2. So the secant of that, the secant square of pi over 4 is just the reciprocal . It's just 2. Okay? This is equal to 2. Basic trigonometry. So here we have 2 times 1 plus y prime equal to 0. Remember, that whole thing is just 0. Okay, solve this for y prime. You can divide by 2. There you get y prime equal to -1. Okay, we just found our derivative. guys. We found the derivative. Okay, this is the derivative at that point, which is, again, this is our slope. So slope m is -1, and the point is pi/8, pi/8. The equation of any line is y minus y1 equal to m x minus x1. Plug in y minus pi/8 equal to -1 times x minus pi/8. Okay, and that's it. You can clean this up. You can solve this for y. If you solve it for y, you're going to get what? You're going to get y equal to -x. Here you have a -1 times -pi/8. That's pi/8. Add this pi/8, you get 2 pi/8 or pi/4. So with calculus problems in our book, guys, the harder the problem looks, the crazier the problem looks, the easier it is actually. Yeah. The crazier the problem, there's got to be something that solves it very quickly. Just keep that in mind. That's like how problems in our book are built, in any calculus class or math class is built. There is a simple solution eventually to the problem. Okay, so again, if you have an implicit equation and they want you to find the derivative at a point, or slope of the tangent line at a point, or the equation of the tangent line at a point, you can always take the derivative using implicit differentiation and not solve for dy dx yet. You can plug the point in. We plug the point in, and then we can solve for dy dx. We get the dy dx. This dy dx is the derivative at that point. It's not the derivative at every point. It's just the derivative at that point. Let's just do one more problem. Section 2.8, number 32. Not gonna write down the whole problem because it's wordy. Actually, it doesn't have a lot of words. It says a kite 100 feet above the ground. So we have a kite 100 feet above. Moves horizontally at a speed of 8 feet per second. That's a related rate, 8 feet per second. Whenever you have distance over time, anything over time, that's a related rate problem. Okay. Question here is, at what rate is the angle between the string and the horizontal They should just say angle of depression. I don't know why they're saying that. Angle of depression. Horizontal decreasing when 200 feet of string has been let out. Okay, so let's draw a picture. We have a person, okay, which is flying the kite. So here's the kite, right? And this is the string. So I'm not drawing the string in solid because it is changing. This is a changing variable. The distance between the kite and the ground does not change. It's always 200. So I'll draw that solid. Okay. What else is changing? This is also changing. You could draw the figure both ways if you want. Okay, so yeah, let's do that. So put the 200 here. Okay, so again, the person, the kite is moving that way. It's moving that way. So, I thought I'd draw it like this. This is use variables. We could call that X. We can call that Z or whatever you want to call it. This is the angle theta. It's the angle made between the string and the horizontal theta. So they're giving you here, oh, the kite is 100 feet away. Sorry, that's 100, not 200. Okay, so they're giving you the rate of x. They say dx dt is equal to 8 feet per second. Okay, the kite is moving. They say it's moving horizontally. It's moving that way. It's not going up, guys. It's not. It's moving horizontally. So it's the rate of x. X is a horizontal component. Yeah, and it's 8 feet per second. The question is, what is d theta dt when 200 feet of string has been paid out? So when z is 200, okay, that's the string, not x. They're not saying what is d theta dt when x is, but z, which is the length of the string. Okay, so here we need a guys, we need a relationship. Okay, we need a relationship that involves theta. Okay, a trigonometric relationship involving theta. Now, the question is, we have so many relationships. We have, for example, we have cosine. Okay, cosine of theta is adjacent over hypotenuse. It's x over z. Cosine, once again, see, cosine of theta is x over z. But guys, I don't want to use this relationship. You don't want to use this relationship because we are not given the rate of z. You can use it, but you're going to have a hard time with it. This has too many variables, guys. It has too many. I don't want to use this relationship. So don't use it because dz dt is not given. Okay, so let's use something else. Maybe we use tangent. Tangent of theta is opposite. Opposite is 100 divided by x. Okay, you can use this relationship. This is a good relationship because it doesn't have too many variables, and dx dt we have. All right, we have dx dt, so this is good. But the only thing, guys, the only thing with this relationship is that when you take the derivative, here you have a quotient. You have 100 divided by x. So you would have to use the quotient rule, and that's not going to look good. So instead, you can use tangent of theta, or not tangent, but cotangent of theta equal to x over 100. This is much better, guys, because I can now put this 100 in front of cotangent theta, and it's just going to be considered as a constant factor. I could do the same thing with this x. I could put the x in front of tangent, but then, guys, if I do that, I have x times tangent theta, which requires the product rule. And I don't want to deal with that. I mean, you could do it, but it's not going to be as easy as this one. Okay, so this is better because, again, we can write that as, let me erase this. We can write that as x equal to 100 cotangent theta. When you take the derivative, 100 is a constant factor. You don't use the product rule. So let's go with that. Take the derivative now. Take d dt, the derivative with respect to t, to get dx dt on the left. On the right, leave the 100 alone. Take the derivative of cotangent. The derivative of cotangent is negative cosecant square of theta, times that by chain rule, times by d theta dt. Don't forget chain rule. With related rates, we got to do chain rule also. Okay, now we plug in. Okay, so now you need to evaluate with the given information. We have dx dt, which is 8. We need d theta dt. I just need to know what cosecant is at that moment. Okay, so when z is equal to 200, draw your triangle. This is theta. That's 200. That side is always 100. Guys, cosecant of the angle, cosecant by definition is hypotenuse divided by what? Hypotenuse by the opposite. Hypotenuse by the opposite. And we have the opposite. It's 100, thankfully. We have both the hypotenuse and the opposite. That's good. So cosecant happens to be 200 over 100, or just 2. Plug that all in into the derivative relationship. Dx dt is 8 equal to negative 100 times cosecant is 200 over 100 squared and d theta dt is the unknown. All right, and you just have to solve this for d theta dt. Here we have 8 equal to negative 200 over 100 is 2 again times 100, negative 200 d theta dt. So d theta dt is negative 8 over 200, or you can reduce that to whatever. Whatever we get, doesn't matter really. But yeah, it is a decreasing value, guys. This derivative is decreasing, and that's because this angle is decreasing. As the kite is moving that way, the angle gets smaller and smaller, okay? So, but this would be a great problem to also review. All right, but when you're choosing a trigonometric relationship for your angle, always use a constant in your relationship. You want a constant because constants are good. You don't have to take their derivative. And use the component whose derivative is already given to you, right? Use x because we have the derivative of x. Again, I can take other relationships like so cosine, or we could take sine. If you do, for example, sine of theta is going to be 100 over z. But again, we don't have the derivative of z, so you don't want to use, guys, we don't want to use anything that has z in it in this case because we don't have the derivative of z. Okay. All right, guys, that's all I could do for today. I know you guys have been here for like 2.5 hours, and I really have to run now. So let's meet again on, I don't know when, like maybe Sunday. By then, hopefully you guys have done most of the problems on the list, so you can ask me questions. Already?